if we wanted to convert that feet into miles, what would we do? Don't forget, you guys can push your space bar and unmute yourself for a second if you want to chime in. Or you can put stuff in the chats. I saw a lot of your hands move like you were going for space bars, but nobody did. Multiply by 1 over 5,280. How do we know we have to multiply by that reciprocal as opposed to just the 5,280? You're absolutely right, though. That is good. So one of the things I want to remind you of is our tool of dimensional analysis. So, why do we multiply by 1 over 5,280? We do that because we're trying to get rid of the units of feet and put in the units of miles, right? So, because we want those feet to cancel, we want to introduce miles. So what we have to know is an equivalency. And Dominic, your 1 over 5,280 is that equivalency between miles and feet. 1 mile is the same as 5,280 feet. I assume you all know that. We're in one of the 3 countries in the world that still use non-metric systems, so of course you all know how many feet are in a mile. I'm glad you're nodding because I do assume that as we go along. So what is the value of this fraction that we're multiplying by? Take a minute and think about that. What is the value of that fraction? Determine the value of that fraction. Think about it for a minute. Put it in the chat or say it to us. I'll get you guys used to communicating here. What is the value of that, of the fraction in this box? What is the value of this fraction? Shay and Dominic throwing out ones. More ones. Good. It is exactly a value of 1. 1 mile and 5,280 feet are the same thing. Anytime you have the same thing in the top and bottom of a fraction, it means it's a 1. How many times does 5,280 feet fit in 1 mile? It fits once. So that's why when we multiply by this, we're not changing the value of this 1,543 feet. All we're doing is changing the language that it's described in. And that's why we need this equivalency. So how many miles is this? Okay, it's whatever the heck 1,543 divided by 5,280 is, whatever that value is. I'm not concerned about what the actual value is, but that process of dimensional analysis allows us to move from one unit to another as long as we know an equivalence. And that's why we needed that 2 pi radians in one rotation, because we know how many degrees are in one rotation. We know 360 degrees is equal to 1 rotation, but we also know that 6.28, that this 2 pi is 1 rotation. So 360 degrees is the same amount of rotation as 2 pi radians. So this is equivalent to us saying that the 5,280 feet is equal to 1, I'd put the M there, 1 mile. So to turn this into the conversion fraction that we used, the 1 over 5,280, we divided that off, 1 mile over 5,280 feet, and that gave us a unit conversion. Hopefully you can see why we call this a unit conversion, because it is 1 unit. It converts our units from one to another. So if we want to do that same thing with degrees to radians, we're going to want to use this equivalence to make ourselves a ratio That can move us from either degrees into radians or from radians into degrees. Now, we could use 360 degrees and 2 pi as the two pieces of that ratio if we wanted to, but we actually don't tend to. This is larger than it has to be. You might notice both sides of these are divisible by 2. So instead of using the 360 degrees and the 2 pi, we will more commonly just use the fact that 180 degrees is equal to pi. Now, this is specifically pi radians. You'll notice I often don't say or write the radians, but you'll notice I always say and or write the degrees. This is important. If we don't write a unit, if I just write, say, 45, I have an angle of 45, is that 45 degrees or 45 radians? Shay, you've gotten trapped by this before. This can burn you a lot. If you don't say something is degrees, because as we talked about, the units cancel on radians, if we don't specifically specify that this is 45 degrees, it is a radian measure. Does that make sense? This is not like, in some courses when they go, oh, you have to put your units down, because if you just say 45, we don't know what that is. You got to say it's feet or meters or whatever. That's certainly true and important, but this is in some ways more significant. If you have an angle and you say it's 45, nothing, you have said it's radians. So it's not that you've left off the unit of measure, you have expressed the wrong one if you meant degrees. So if we want this to be 45 degrees, we have to put that degree symbol or write the word degrees, and we should say it as well. If we don't, it's radians whether we say it or not. Speaking of 45 radians might seem like a lot for radians, and it is. 6 radians is a full rotation. So 45, well, 6 1/4, a little more than 6 1/4 radians is a full rotation. So 45 is going to be like 6 or 7 rotations to get 45 radians. But can things spin 6 times? Sure, you can go through hundreds, thousands, millions of degrees of rotation. We can have radian measures get as high as we want. So 45 radians is not unreasonable, but it's easy to think that's degrees if nobody tells you. So we have to make sure we label it properly. So like here, I didn't write radians here. Don't have to. This is an angle measure. It's equal to another object. It has to be an angle measure with no label. It has to be radians. Fair? So be careful about that as we go along. So this equivalency, pi radians being equal to 180 degrees, is going to allow us to convert from any radian measure to any degree measure and back and forth. So let's use this. Let's say we want to turn 45 degrees, since we're talking about 45 so much. We want to turn 45 degrees into a radian measure. Well, we're going to use that same dimensional analysis tool. If we want to get rid of degrees, we need degrees to be down here on the bottom, so they cancel like the feet did before. If we're trying to introduce radians, again, we don't have to label it, but it's handy. We need radians to be introduced on top. Then our degrees will cancel, we'll be left with radians. All we need is this equivalency between degrees and radians. So how many degrees? 180 is the same as how many radians? Pi. This conversion factor, this conversion ratio, will divide out our amount of radians, our amount of degrees, put us into radians, and we'll have a nice measure. So 45, don't have to write the degrees because they canceled out. So 45 pi over 180, which will reduce to pi over 4 radians. Now we can certainly approximate that, something like 0.78 or points, doesn't matter. But we'll tend to leave it in exact values. We like exact values, particularly when you're measuring angles. Small inaccuracies over long distances with angles can cause lots of error. So we will tend to use exact values when possible, particularly for radian measures. We will tend to approximate degrees because degrees suck anyway, and stay exact when we're dealing in radians. So pi over 4 radians, that's a 45-degree angle. So if we wanted to put it on our diagram even, if this is a 0, and we will tend to do this, we will tend to put, measure our angles in what's called standard position. We'll put our 0 on the horizontal, where it would be the positive x-axis, and measure angles positively in the counterclockwise direction and measure our angles negatively in the clockwise direction. So in standard position, that's our pi over 4, our pi over 4 radians. If you're curious, yes, there are negative angles. If we go through an angle of, say, 70 degrees and then go backwards 10 degrees, that's a negative 10-degree angle to get us to 60 degrees. So we will talk about angles being negative quite often. What if we wanted to go the other way? What if we had, let's just even go with 1 radian. Say we wanted to know how many degrees approximately is 1 radian. Well, we'd do the same thing. But the difference here is we'd have to be canceling out radians. So we'd want radians down there and introducing degrees. So the only difference is which one's going to go where. A lot of people try to do this by kind of memorizing. We go, pi over 180 when we go from degrees to radians, and we do 180 over pi when we're going from radians to degrees. I don't like the idea of memorizing which one of those, which ratio to use when. It's easier to use the dimensional analysis. The idea that we're trying to get rid of degrees means that degree has to be on the bottom. The fact that we're trying to get rid of radians here means that radians has to be on the bottom. That way, all we have to know is this equivalency, and we don't have to really remember which orientation we use when. Use the units to tell you which orientation it has to be in. You really want to try to memorize as little as possible. So, but that would end up getting rid of the radian measures. We'd end up with 180 degrees over pi, which if we wanted to stay exact, we'd just have to leave it there. But, a nice decimal approximation would probably be handy. You guys have calculators out there probably, right? Who has a calculator? A couple of you. Good. Take 180 degrees, divide it by pi. Tell us what that measure is. I know about what it is, but I don't always remember all the decimals. It's like 57 something, I think. Oh, there we go. 57.29577, so on. This will go on forever. It will be an irrational number, but I'm going to round it to there. So round it to there. So 57, how about 0.3 degrees? Ish. So, how much is 1 radian in degrees? It's about 57.3. It's a little bit less. And again, that should seem reasonable in scale. When we had the 1 radian was about there. So for that length being equal to that length, and 57 about 60 degrees seems reasonable there, I should hope. Cool. So wherever it was, who asked that? Martin, you asked about going from radians to degrees. This conversion factor in either orientation is what's going to get you to move between any of them. Now, the example I did down here moved a kind of a whole number of radians into an amount of degrees. But often when we see radians, they often look like this one does. They often look like cuts of pi. So it's really common to see things like, oh, I don't know, a 7 pi over 12 radian angle. Any clean cut of a circle is going to have that pi in it. Do be careful. Not all our radian measures have a pi in it. That 45 radians, there was no pi in there. All that means is it's not an even cut. But we, when we started, we defined 1, 2, 3 radians. It's just when we try to divide this up into even pieces that pi has to come in. So it's very common to see radians without a pi in it, but it's also extremely common to see that pi. But if we wanted to convert that radians into degrees, we'd be doing the same thing. We'd be canceling out the radians and putting it in degrees. You'll notice as we do more dimensional analysis, I always write the units first, because that's the important part. That's what's guiding our process. So writing your units first is a good habit. So if we're getting rid of radians and putting in degrees, then 180 has to go up there and the pi has to go down there. It is always nice when this happens because the pi's cancel. So 7 times 180 over 12 degrees. We just got to figure out what this is. I don't know, it's 180, that's 6 and 90. So 3 and 45. So 15 and 1. So 70 plus 35. It's what, 105 degrees? Does that work? I really do want to remind you and encourage you I know your book, most books do kind of break it up into 2 pieces. Like when you're going from degrees to radians, use this ratio. When you're going from radians to degrees, use this ratio. I don't like that. Use this equivalency. If you remember this, on the equivalency, you can move back and forth between radians and degrees all you want. Just like if you know this equivalency between miles and feet, you can go between miles and feet all you want. Fair? All right. Do I prefer exact answers or decimal approximations? I prefer exact answers. We will give exact answers almost whenever possible. As I said, with decimals, we will tend to give, with degrees, we'll tend to give decimal approximations because just that's the nature of using degrees. If somebody gave me an answer that this was 180 degrees over pi, 180 over pi degrees, if I didn't tell you to approximate it, I would love seeing 180 over pi degrees. Because what that tells me is that you're comfortable with exact answers. Fair? But oftentimes when an answer is going to be in degrees, your tests or your homework will say approximate it to 1 degree or another. But particularly when we're working in radians, and particularly when we're working with a lot of the values we do, we will try to stay exact as much as possible. So push yourself to answering exact whenever you can. But do make sure that you're reading the instructions on your problems that say what form it wants. Okay? But really, if you can get in the habit of working in exact answers, you're going to be happier as we go along. Oftentimes, by the end of this course, people get sick of approximating. They just get used to moving around these, pies and square roots and not having to carry around these big decimal approximations, carrying around, the square root of 3 pi over 8, moving that symbol around is much easier than moving around a big decimal and trying to handle the cumbersome decimal once you get used to doing it. So it is a nice habit to get into. Ooh, I need a bigger eraser tool. I wonder if there's a way to set that up. Actually, I can probably do this. That might have made me a little too happy. Okay, so it's just what's encased in it. Interesting. Nice, that makes me happy. It is good to be easily made happy. So, we got a couple minutes left. One of the goals that we have early on here is to start teaching ourselves to think in terms of radians. You have a lot of experience, whether passive or active, dealing with degrees. If I tell you I've got a 160-degree angle, you've probably got a fairly good sense of about how much 160 degrees is. Could you lay it out perfectly? Probably not. But could if you had, like, if I said 160 degrees, you'd say no. If I said 160 degrees is that, you'd say no. Because you've got a sense of, you're roughly 160 degrees should be, a fairly good obtuse angle, right? But if I say a 17 pi over 6 angle, you likely don't have any visualization or any idea what 17 pi over, I forgot what I said. Let's go with 6. What 17 pi over 6, how much angle measurement that is, roughly. So learning to think in radians a bit is one of our first jobs. So to do that, there's a nice exercise that I want you guys to all do, repeatedly, build this thing several times because we'll use it quite a bit. To build this, we do need a circle and an axis in there. As I said, in standard position, we will start all of our angle measurements from this kind of positive x-axis location. And if we start there, as I said, we measure positively in the counterclockwise direction, so measuring up for positive, down when we're measuring angles negatively. Do notice that does mean we go first through quadrant 1, then through quadrant 2, then quadrant 3, and lastly quadrant 4 before returning back to quadrant 1. If you've ever been thrown off by the quadrants being numbered in this way, it's kind of a weird way to number quadrants. This is why the quadrants are numbered this way, because it is the order of our rotation. So if we want to think of our circle in terms of radian measure, we're going to start 0 here and go all the way around. How many radians were there in that full rotation? Actually, no, let somebody either say that or type that. How many radians were there in that full rotation? Chris, oh, you even got a nice pi symbol on yours. Awesome. So 2 pi radians in that full rotation. So if there are 2 pi radians in the full rotation, that means a half rotation should have pi radians. I don't know why I wrote it that way. And that's the same as our 180 degrees is the same as pi radians. So half a rotation is going to be pi radians. That means half of that should be half of pi. So if we measure from here to here, what we think of as 90 degrees, what we think of as a right angle, is the same as pi over 2 radians. So we might even start saying, instead of a 90-degree right triangle, it's a pi over 2 right angle. If we take half of that, half of pi over 2, is pi over 4. That's our 45-degree angle. We calculated that a minute ago. And it sits nicely as that half length. Now we could keep going and say half of that is pi over 8, but it turns out pi over 8 is not terribly useful. We'll talk about why they're useful or not probably tomorrow. But pi over 8 doesn't end up being all that useful. So I want to stick with this pi over 4 for a minute, and I want to count this pi over 4 around the circle. What do I mean by count? Let's do that. So if this is 1 pi over 4 radians, this would be 2 of those, so 2 pi over 4. Notice 2 pi over 4 would reduce to pi over 2. If we thought of this as 2 pi over 4, it would be the same. If we go another pi over 4 radians, we'd be at 3 pi over 4 radians. 1 pi over 4, 2 pi over 4, 3 pi over 4 radians. Equivalent to 135 degrees if you want. But I want to get used to thinking about these without having to think about the degree measure. So 3 pi over 4, 3 pi over 4 is that measure. Less than straight, less than straight, so it's less than pi. 3/4 is less than pi. But it's certainly in quadrant 2 because it's bigger than half of pi. 3/4 is bigger than half. If we keep going, add another pi over 4, we'll get to 4 pi over 4. 4 pi over 4 reduces to pi. How many pi over 4s are down here? I'm going to assume you all, in one loud voice, shouted 5. Some of you typed 5. Awesome. 5 pi over 4 down there. 6 pi over 4. We could reduce the 6 pi over 4 to 3 pi over 2. We will here. And we could have counted pi over 2s too. 1 pi over 2, 2 pi over 2, 3 pi over 2. So that would have worked. So 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. 8 pi over 4 is 2 pi. We could keep going. 9 pi over 4, 10 pi over 4, 8 pi, 9 pi over 4, 10 pi over 4. We could keep counting those pi over 4s around as much as we want. We also want to be able to break these into even smaller pieces. But instead of the pi over 8s, what's actually handy is to, instead of break this pi over 2 in half, break that pi over 2 into thirds. So a third of pi over 2 would be a pi over 6. So this is a pi over 6 radian angle. And I got to let you go here in a minute, but I want to count those around real quick. So the same idea, 1 pi over 6, and then 2 pi over 6, which we will reduce in a minute. But 1 pi over 6 radians, 2 pi over 6, 3 pi over 6, which reduces, 4 pi over 6 radians, 5 pi over 6 radians, 6 pi over 6, which would reduce to pi, 7 pi over 6 radians, 8 pi over 6 radians, which will reduce, 9 pi over 6 would reduce to the 3 pi over 2, 10 pi over 6 radians, and 11 pi over 6 radians allows us to count the pi over 6s all the way around. It is good to reduce these. Think of this as a pi over 3 radians, 2 pi over 3 radians, 4 pi over 3 radians, which we could have counted the pi over 3s. I think counting the pi over 6s is nicer. 5 pi over 3. And again, our 12 pi over 6 reduces to our 2 pi. So making this diagram yourself, building this diagram using this counting method can be a really handy way to start getting used to the idea of radians and used to the idea of thinking in radians. Because then when somebody does come along and say, hey, how much rotation is 17 pi over 6? And you say, I don't know. You go, well, how many pi over 6s are there in a full rotation? Well, there are 12 pi over 6 in a full rotation, right? Or we could count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 13, 14, 15, 16, 17. So 17 pi over 6 is a full rotation, the 12, and then another 5. So 17 pi over 6 lands in the same place as 5 pi over 6. We even call those coterminal, is same terminal end. So it's coterminal to the 5 pi over 6. And getting used to thinking in terms of diagrams like this will go a long way into getting us to be able to think and understand more in radian measure. You guys got any questions about that? Do go practice doing this. A fair amount of you went into the discussion boards with your introductions. That was great. If you haven't done that, please do that. Also, please start playing with the homework for 6-1. There's a lot in 6-1. We'll spend at least one more day talking about it, and then start talking about 6-3. So if there's anything anybody needs, let me know. Prodigious silence. I'm going to hope you're all happy. And if you're not, please send me an email, send me a message. Let me know how I can help. I'll talk to you guys tomorrow. Have a great day. Not exactly sure why I'm erasing the board at the end of class. It's just kind of a habit. An excuse to kind of stand around and see if anybody has any questions they didn't want to ask while everybody was here. Hope you guys all good. Okay. I'll sign you off. I'll see you guys tomorrow.